Hi, my name is Cole Chapman, and I'm a junior from Greensboro, North Carolina. I'm currently pursuing a major in chemistry along with a minor in entrepreneurship. And I want to become a chemistry mentor for one, obviously, I have a great passion for chemistry, and it's something that I greatly enjoy, and it's something I see myself doing for my future. Along with this, I've also had a very positive experience with the chemistry mentor program throughout my chemistry career. Um, with all the mentors that I've had, they've been integral in helping me better understand chemistry and developing the passion that I now have for chemistry. And I really hope to spread that passion to fellow students because that passion has led me to decide to become a chemistry major and pursue something in that field. And I really hope that I have the capability to do that to other fellow students. So with that being said, here is a fun chemistry problem that you can watch me explain. All right, so the first step of solving any reaction is simply just to look and see at what you've been given. So in this case, we have a cyclohexene reacting with methanol and catalytic sulfuric acid. So as it sits right now, we have a nucleophile with this cyclohexene due to the extra pair of electrons in the double bond, but we don't have an electrophile. So as it sits right now, there's nothing to start this reaction, and that's why the sulfuric acid is present. Sulfuric acid is a very strong acid, meaning that it likes to donate protons. And so in that case, it's going to donate protons to this methanol. And when that happens, you form protonated methanol. And protonated methanol, that has a pKa of around -3. And this pKa of methanol that's not protonated has a pKa of about 15. So now we have a much stronger electrophile with protonated methanol to react with this nucleophile. So with that being said, they're going to react. So the nucleophile is going to want to grab this hydrogen from this electrophile. It's going to donate those electrons back to the oxygen, and now that double bond is gone. And now we have a decision to make. With that double bond being gone, the hydrogen has to bond to this carbon or this carbon. So it can form the tertiary carbon or the secondary carbon. But we want a tertiary carbocation. Tertiary carbocations are much more stable than secondary carbocations. So that means we're going to want to form the carbocation right there, and the hydrogen has to bond right there. But even still, now this molecule is still not very happy. And we have all this methanol still floating around in solution. So with that being said, methanol is going to come back and react. And in this case, it's going to form a new asymmetric center. So methanol is going to attack from the top and the bottom. So with the top attack, methanol is going to bond, but now that oxygen is going to be positive due to the new bond formed. In an electronegative element like oxygen, that positive charge is not very happy on that molecule. So now we still have more methanol in solution, and methanol is going to come back and it's going to grab that hydrogen and donate its electrons back to that oxygen to put a lone pair in the oxygen to get rid of that positive charge. And not only does it get rid of that positive charge, as you'll see right here with this OCH3 and CH3, but when this methanol goes in and grabs that hydrogen, now we form more protonated methanol, and that's going to allow the reaction to keep going and keep going. And so we'll see with the bottom attack, it's the same thing, just the different orientation. Methanol is going to attack from the bottom, so the CH3 group, the methyl group, is going to be on the top, and now methanol is going to attack from the bottom. We still have this positive charge on oxygen due to the new bond being formed, and it's still not happy. So methanol is going to come back in. It's going to grab this hydrogen, donate those electrons back to oxygen to form a lone pair on oxygen. And we're going to get rid of that positive charge on that oxygen. And we're going to regenerate protonated methanol again. So in this case, we form a racemic mixture due to the new asymmetric center being formed, where the OCH3 group bonds from the top or from the bottom, and protonated methanol is formed again to allow this reaction to keep going.